Welcome back. Today, we're exploring a fascinating feature of Python, decorators. Decorators are really useful in different topics, for example, logging, authentication, and memorization. Personally, I haven't used decorators, but they have some useful use cases, so I did my best to learn how to use them. By the end of our session, you'll understand not only how to implement decorators using the familiar syntax, but also how to leverage them to optimize your functions and overall workflow. Let's jump right in. Let's start with the basics. A decorator in Python is a design pattern that allows you to modify or extend the behavior of a function without changing its code. Think of it like wrapping a gift and adding something special without altering what's inside. Here's a simple example of a decorator that adds a message before calling a function. In this example, when you call say hello, Python applies the myDecorator decorator, which returns a new function, wrapper, that first prints an extra message and then calls the original say hello function. Decorators are a powerful way to enhance or modify the behavior of functions without duplicating code. For example, you can also add behavior after the function runs. In this modified example, the decorator adds an extra action both before and after the execution of say hello, demonstrating just how flexible decorators can be for streamlining code and handling cross-cutting concerns like logging or authentication. Now that we know what decorators are, let's talk about memoization. Memoization is a technique that saves the result of an expensive function call and reuses them when the same input occurs again. This is especially useful for functions with repeated calls, like recursive calculations. For example, calculating Fibonacci numbers can be very slow without memoization, because the same numbers are recalculated multiple times. Memoization ensures we only compute each value once. Let's write a decorator that adds memoization to a function. We'll use a dictionary to store the results of previous calls. Whenever the function is called, the decorator checks if the result is already stored. If it is, it returns the cached value instead of recalculating it. Here's how it works. The memoize decorator wraps the Fibonacci function. It then uses a dictionary cache to store results for specific inputs. Before calculating a result, it checks if the input is already in the cache. If it is, it retrieves the result instantly. If not, it calculates the result, stores it in the cache, and then returns it. Notice how much faster the function becomes as it avoids redundant calculations. As we saw in previous videos, Python's built-in LRU cache decorator from the functools module essentially does the same thing, caching function results to speed up repeated calls. It even manages the cache size automatically using a least recently used strategy. That's where the LRU comes from. It's fascinating to think about how these behind-the-scenes optimizations work to enhance performance. Let's build a logging decorator that tracks function calls. This decorator logs essential details each time the function is evoked, displaying the function's name, the arguments passed, and the value it returns. This is a great tool for debugging and understanding your code's behavior. Here's what happens in this example. The log decorator wraps target function. Before executing the function, it logs the function name and its arguments. After the function runs, it logs the return value. This approach is invaluable for debugging and monitoring how functions behave in your code. Now, let's create an authentication decorator. This decorator checks if a user is authenticated before allowing access to a function that handles sensitive operations. If the user isn't authenticated, the function won't run, and the warning message will be displayed. In this example, the requires authentication decorator wraps a function that expects a user dictionary as its first argument. Before executing the function, it checks if the authenticated key in the user's dictionary is true. If not, it prints a warning message and prevents the function from running. This decorator provides a simple yet effective way to incorporate access control into your code, ensuring that only authenticated users can perform certain actions. Now that we've seen decorators in action for memoization, logging, and authentication individually, let's put it all together in a practical example. We'll create a function that simulates retrieving user data, a task that might be both resource-intensive and sensitive. By stacking decorators, we can ensure the function logs its calls, caches results to speed up repeated requests, and restricts access to authenticated users only. Take a look at this composite example. In this example, authentication check, the requires authentication decorator, ensures that only users with an authenticated status can proceed. Caching. The memoized decorator caches results based on a unique key composed of the username and function arguments, avoiding redundant processing. Logging. The log decorator prints details of each call, including the function name, arguments, and returned results. By stacking these decorators, we enhance getUserData without cluttering its core logic. This layered approach not only makes our code cleaner, but also demonstrates how decorators can be combined to create powerful, modular functionality in real-world scenarios. Today, we unlock the power of decorators by exploring three key techniques: memoization, either through a custom decorator or Python's built-in LRU cache, can drastically speed up repeated function calls. Logging. We built a logging decorator that tracks every call, capturing input and outputs to help you debug and understand your code's flow. Authentication. We implemented an authentication decorator to secure sensitive functions, ensuring that only authenticated users can access certain operations. You can even include this kind of logic in, for example, a CLI tool. Here's an idea. We then brought these ideas together in a practical example, stacking these decorators to create a robust, efficient, and secure function for retrieving user data. Well, this is something that came to mind when I was editing the video. In the example, it may seem confusing. How is it faster to memoize or don't memoize? But as you can see, we use time sleep here in the getUserData function. This is to simulate how a real-world server will take some time to respond. If we already have that value cached, we wouldn't need to wait. This layered approach not only keeps your core logic clean, but also demonstrates how powerful and modular your code can become when you combine these techniques. Now it's your turn to put these concepts into practice. Experiment by writing your own decorators, try combining memoization, logging, and authentication in your projects. If you enjoyed this video, don't forget to like, subscribe, and share your thoughts in the comments below. In our next episode, we'll dive into JSON and SQLite databases, taking another step towards building powerful Python applications. See you in the next dimension.